X-ray spectroscopy is a gathering name for several spectroscopic techniques for characterization of materials by using X-ray excitation. Characteristic X-ray spectroscopy. When an electron from the inner shell of an atom is excited by the energy of a photon, it moves to a higher energy level. When it returns a low energy level, the energy which is previously gained by the excitation is emitted as a photon which has a wavelength that is characteristic for the element. Analysis of the X-ray emission spectrum produces qualitative results about elemental composition of the specimen. Comparison of spectrum of the specimen with spectra of standards of known composition produces quantitative results. X-rays can be excited by a high-energy beam of charged particles such as electrons or protons, or a beam of X-rays. These methods enable elements from the entire periodic table to be analyzed with the exception of H, He and Li. In electron microscopy, electron beam excites X-rays. There are two main techniques for analysis of spectrum of characteristic X-ray radiation: energy dispersive X-ray spectroscopy and wavelength dispersive X-ray spectroscopy. Energy dispersive X-ray spectroscopy. In an energy dispersive X-ray spectrometer, a semiconductor detector measures energy of incoming photons. To maintain detector integrity and resolution, it should be cooled with liquid nitrogen or by Peltier cooling. EDS is widely employed in electron microscopes and in cheaper or portable XRF units. Wavelength dispersive X-ray spectroscopy. In a wavelength dispersive X-ray spectrometer, the single crystal diffracts the photons which are collected by a detector. Without any motion, there will be just one wavelength detected. By moving crystal and detector, a wide region of spectrum is observed. In contrast to EDS, WDS method is a method of sequential spectrum acquisition. While WDS is slower than EDS and more sensitive to positioning specimen in the spectrometer, it has superior spectral resolution and sensitivity. WDS is widely used in microprobes and in XRF. It is widely used in the field of X-ray diffraction to calculate various data such as INTERPLANER spacing, wavelength of incident X-ray by using Bragg's law. X-ray emission spectroscopy. William Lawrence Bragg and William Henry Bragg, who were the 1915 Nobel Prize winners, were the original pioneers in developing X-ray emission spectroscopy. He measured the X-ray wavelengths of many elements to high precision, using high-energy electrons as excitation source. He also painstakingly produced numerous diamond-ruled glass diffraction gratings for his spectrometers. Intense and wavelength-tunable X-rays are now typically generated with synchrotrons. In a material, the X-rays may suffer an energy loss compared to the incoming beam. This energy loss of the re-emerging beam reflects an internal excitation of the atomic system, an X-ray analog to the well-known Raman spectroscopy that is widely used in the optical region. In the X-ray region, there is sufficient energy to probe changes in the electronic state. For instance, in the ultra-soft X-ray region, crystal field excitations give rise to the energy loss. The photon-in photon-out process may be thought of as a scattering event, when the X-ray energy corresponds to the binding energy of a core-level electron. This scattering process is resonantly enhanced by many orders of magnitude. This type of X-ray emission spectroscopy is often referred to as resonant inelastic X-ray scattering. Due to the wide separation of orbital energies of the core levels, it is possible to select a certain atom of interest. The small spatial extent of core-level orbitals forces the Rix's process to reflect the electronic structure in close vicinity of the chosen atom. Thus Rix's experiments give valuable information about the local electronic structure of complex systems, and theoretical calculations are relatively simple to perform. Instrumentation. There exist several efficient designs for analyzing an X-ray emission spectrum in the ultra-soft X-ray region. The figure of merit for such instruments is the spectral throughput, i.e., the product of detected intensity and spectral resolving power. Usually, it is possible to change the parameters within a certain range while keeping their product constant. Grating spectrometers. Usually X-ray diffraction in spectrometers is achieved on crystals, but in grating spectrometers, the X-rays emerging from a sample must pass a source-defining slit. Then optical elements disperse them by diffraction according to their wavelength, and, finally, a detector is placed at their focal points. Spherical grating mounts. Henry Augustus Rowland devised an instrument that allowed the use of a single optical element that combines diffraction and focusing. A spherical grating. Reflectivity of X-rays is low regardless of the used material, and therefore grazing incidence upon the grating is necessary. X-ray beams impinging on a smooth surface at a few degrees glancing angle of incidence undergo external total reflection, which is taken advantage of to enhance the instrumental efficiency substantially. Denote by r the radius of a spherical grating. Imagine a circle with half the radius r tangent to the center of the grating surface. This small circle is called the Rowland circle. If the entrance slit is anywhere on this circle, then a beam passing the slit and striking the grating will be split into a specularly reflected beam, and beams of all diffraction orders that come into focus at certain points on the same circle. Plane grating mounts. Similar to optical spectrometers, a plane grating spectrometer first needs optics that turns the divergent rays emitted by the X-ray source into a parallel beam. This may be achieved by using a parabolic mirror. The parallel rays emerging from this mirror strike a plane grating at the same angle and are diffracted according to their wavelength. A second parabolic mirror then collects the diffracted rays at a certain angle and creates an image on a detector. A spectrum within a certain wavelength range can be recorded simultaneously by using a two-dimensional position-sensitive detector such as a microchannel photomultiplier plate or an X-ray sensitive CCD chip. Interferometers. Instead of using the concept of multiple beam interference that gratings produce, the two rays may simply interfere. By recording the intensity of two such collinearly at some fixed point and changing their relative phase, one obtains an intensity spectrum as a function of path length difference. One can show that this is equivalent to a Fourier transformed spectrum as a function of frequency. The highest recordable frequency of such a spectrum is dependent on the minimum step size chosen in the scan, and the frequency resolution depends on the maximum path length difference achieved. The latter feature allows a much more compact design for achieving high resolution than for a grating spectrometer because X-ray wavelengths are small compared to attainable path length differences. Early history of X-ray spectroscopy in the U.S. Philips glow eye lamp and Fbouquet, headquartered in Eindhoven in the Netherlands, got its start as a manufacturer of light bulbs, but quickly evolved until it is now one of the leading manufacturers of electrical apparatus, electronics, and related products including X-ray equipment. It also has had one of the world's largest R&D labs. In 1941, Holland was overrun by Hitler's Germany. Somehow the company was able to transfer a substantial sum of money to a company that it set up as an R&D laboratory in an estate in Irvington on the Hudson in NY. As an extension to their work on light bulbs, the Dutch company had developed a line of X-ray tubes for medical applications that were conveniently powered by transformers. The X-ray tubes could also be used in scientific X-ray instrumentations, but there was very little commercial demand for the latter. So, the management decided to try to develop this market and set up development groups in their research labs in both Holland and the US. They hired Drive Ira Duffendak, a professor at University of Michigan and a world expert on infrared research, to head the lab and to hire a staff. In 1951 he hired Drive David Miller as assistant director of research. Dr. Miller had done research on X-ray instrumentation at Washington University in St. Louis. Dr. Duff Endak also hired Drive Bill Parrish, a well-known researcher in X-ray diffraction, to head up the section of the lab on X-ray instrumental development. X-ray diffraction units were widely used in academic research departments to do crystal analysis. An essential component of a diffraction unit was a very accurate angle measuring device known as a goniometer. Such units were not commercially available, so each investigator had to try to make their own. Dr. Parrish decided this would be a good device to use to generate an instrumental market, so his group designed and learned how to manufacture a goniometer. This market developed quickly and, with the readily available tubes and power supplies, a complete diffraction unit was made available and was successfully marketed. The U.S. management did not want the laboratory to be converted to a manufacturing unit, so it decided to set up a commercial unit to further develop the X-ray instrumentation market. In 1953, Norelco Electronics was established in Mount Vernon, New York, dedicated to the sale and support of X-ray instrumentation. It included a sales staff, a manufacturing group, an engineering department, and an applications lab. Dr. Miller was transferred from the lab to head up to the engineering department. The sales staff sponsored 3 schools a year, one in Mount Vernon, one in Denver, and one in San Francisco. The week-long school curricula reviewed the basics of X-ray instrumentation and the specific application of Norelco products. The faculty were members of the engineering department and academic consultants. The schools were well attended by academic and industrial R&D scientists. The engineering department was also a new products development group. It added an X-ray spectrograph to the product line very quickly and contributed other related products for the next 8 years. The applications lab was an essential sales tool. When the spectrograph was introduced as a quick and accurate analytical chemistry device, it met with widespread skepticism. All research facilities had a chemistry department and analytical analysis was done by wet chemistry methods. The idea of doing it by physics instrumentation was considered suspect. To overcome this bias, the salesman would ask a prospective customer for a task the customer was doing by wet methods. The task would be given to the applications lab and they would demonstrate how accurately and quickly it could be done using the X-ray units. This proved to be a very strong sales tool, particularly when the results were published in the Norelco Reporter, a technical journal issued monthly by the company with wide distribution to commercial and academic institutions. An X-ray spectrograph consists of a high-voltage power supply, a broadband X-ray tube, usually with a tungsten anode and a beryllium window, a specimen holder, an analyzing crystal, a goniometer, and an X-ray detector device. These are arranged as shown in Fig. 1. Fig. 1. The continuous X spectrum emitted from the tube irradiates the specimen and excites the characteristic spectral X-ray lines in the specimen. Each of the 92 elements emits a characteristic spectrum. Unlike the optical spectrum, the X-ray spectrum is quite simple. The strongest line, usually the alpha line but sometimes the alpha line, suffices to identify the element. The existence of a particular line betrays the existence of an element, and the intensity is proportional to the amount of the particular element in the specimen. The characteristic lines are reflected from a crystal, the analyzer, under an angle that is given by the Bragg condition. The crystal samples all the diffraction angles theta by rotation, while the detector rotates over the corresponding angle to theta. With a sensitive detector, the X-ray photons are counted individually, by stepping the detectors along the angle, and leaving it in position for a known time. The number of counts at each angular position gives the line intensity. These counts may be plotted on a curve by an appropriate display unit. The characteristic X-rays come out at specific angles, and since the angular position for every X-ray spectral line is known and recorded, it is easy to find the sample's composition. A chart for a scan of a molybdenum specimen is shown in Fig. 2. The tall peak on the left side is the characteristic alpha line at a 2 theta of 12 degrees. Second and third order lines also appear. Fig. 2. Since the alpha line is often the only line of interest in many industrial applications, the final device in the Norelco X-ray spectrographic instrument line was the Interferometer. This device could be programmed to automatically read at any desired 2 theta angle for any desired time interval. Soon after the Interferometer was introduced, Philips decided to stop trying to market X-ray instruments developed in both US and Europe and settled on offering only the Eindhoven line of instruments. In 1961, during the development of the Interferometer, Norelco was given a subcontract from the Jet Propulsion Lab. The lab was working on the instrument package for the Surveyor spaceship. The composition of the Moon's surface was of major interest, and the use of an X-ray detection instrument was a possible solution. Working with a power limit of 30 watts was very challenging, but a device was delivered, but it wasn't used. Later NASA developments did lead to an X-ray spectrographic unit that did make the desired moon soil analysis. The Norelco efforts faded, but the use of X-ray spectroscopy in units known as XRF instruments continued to grow. With a boost from NASA, units were finally reduced to handheld size and are seeing widespread use. Units are available from Bouquet, Thermo Scientific, Elvatech Limited, and Spectro. Other types of X-ray spectroscopy: X-ray absorption spectroscopy, X-ray magnetic circular dichroism,